2017 mock walkthrough. These are the multiple choice answers. Which element is in the D block of the periodic table? You need to go through and you need to see where they all are in the periodic table. If you find selenium, you will see it's in the P block. Antimony is in the P block. Tantalum is in the D block, and lead is in the P block. So there's only one that's in the D block, so C is your correct answer. So which species contains an element with an oxidation state of +4? So the best way to approach this question is to work out the oxidation state of each of the different options. So if we have a look here, we've got oxygen, which is -2. We've got 2 of them, so that makes -4. We've got to go from -4 to +1, so we must be adding 5. So the oxidation state of nitrogen here is +5 and oxygen is -2. So that's not the correct answer. If we do the same for all of the others, and we find this chlorine is +5, the oxygen is still -2, the hydrogen is +1, the sulfur is +4, and the oxygen is -2, and for the phosphorus that's +5, and the chloride is -1. So the one that contains one with +4 is the sulfur in this particular substance, so C is the correct answer. There are 392 mole of pure gold in a bar measuring 10 centimetres by 10 centimetres by 40 centimetres. What is the density of gold in kilograms per decimetre cubed? So the first thing you need to know is an equation for density. So density is equal to mass divided by volume. We need to find out the relationship between mass and moles. In this case, mass is going to be equal to moles times AR. We know how many moles because it's given to us in the question. And the relative atomic mass of gold is from the periodic table is 197.0, which gives me an answer in grams of 77224 grams. We know the answer has to be in kilograms per decimetre, so if I divide that by 1,000, I can convert it to kilograms. Then I need to substitute it into the density calculation. So it's going to be the mass that I've just worked out in kilograms divided by the volume, and the volume needs to be in decimetres cubed. So to go from centimetres to decimetres cubed, you divide by 10, so that would be 1, that would be 1, and that would be 4. So it's going to be 1 times 1 times 4, which is equal to 19.3 kilograms per decimetre cubed. And that is answer B. Ions of 2 isotopes of iron are shown below. Which statement is correct? So the first one, the ions of both of the isotopes have the electron configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Well, if they're transition metal ions, that means when the ion is formed, they lose the s electron first. So if there's s electrons in the electron configuration for the ion, that's not going to be correct, because the s will be lost first. So it's not that option. The ions of the isotopes contain 26 neutrons. Well, we can work out how many neutrons they have. The first one has got a mass number of 53. It's going to have an atomic number of 26. You get that from the periodic table. Mass number times atomic number gives you the number of neutrons. So it's 27 for the first one and 30 for the second one. To be honest, you didn't need to work that out, because any question that has 2 isotopes can be worked out simply by knowing that 2 isotopes of the same element have the same number of protons and a different number of neutrons, so it's obviously got to be incorrect. Okay, the next one says 53 Fe2+ has fewer protons than 56 Fe2+. All atoms and ions are going to have the same number of protons. So that leaves the last one. After acceleration to the same kinetic energy, 56 Fe2 plus will move more slowly than 53 Fe2 plus. An ion with a larger mass will move more slowly. If we look at the relationship, kV equals half mv squared. So the relationship between velocity and mass is inverse. So basically, the higher the mass, the lower the velocity. The successive ionisation energies for the element X are shown in figure 3. Which element is X? Okay, so we need to have a look and see what's going on. So we're going to take the outer electrons first. Now there are 3 outer electrons, and then there's a big jump in energy. And then you've got the next electrons. That suggests there's 3 in the outer shell. So we're looking for a group 3 element. Aluminium's the only group 3 element that's there. Except boron. Boron's also group 3, so let's have a look at this. So nitrogen's group 5, so it can't be that one because it hasn't got 5 electrons in its outer shell. Phosphorus is group 5, so it can't be that one. Boron only has 5 electrons in total. This one's got 1, 2, 3, 4, 5, 6, 7, at least 8 electrons, so it can't be boron, which means it must be aluminium. Which of these decreases down group 2? So the first ionisation energy is going to decrease because the outer electron is getting further away from the nucleus, so it's going to be easier to remove. So that decreases. That looks like that's the answer, but let's check the others. As we go down the group, the atomic radius is going to get bigger. The number of protons is going to increase. And for both group 1 and group 2, their reactivity with water increases. The reason for that is when they react, they lose that outer electron. As you go down the group, it is easier to lose the outer electron because it's further away. Refer to the unbalanced equation below when answering questions 16 and 17. In the balanced equation, the mole ratio for sulfuric acid to water is... So the first thing we've got to do is balance this equation. Okay, so we've got 2 chromiums, 2 chromiums. We've got 3 of those, so we're going to need 3 of those. So we're going to need to have 4 of those and 7 of those. If you're still struggling balancing equations, it's worth coming along to one of the workshops just to spend a little bit of time on it. So that means our mole ratio must be C, which is 4 to 7. Which substance exists as a macromolecular molecule, or a macromolecule? Well, that one is a metal. So it's going to exist as a metallic lattice. Silicon dioxide is very like diamond in its structure. So that's macromolecular. Just have to learn that one. Phosphorus oxide, again, you've got to learn, is a simple molecule. Magnesium oxide is ionic. So that's a learning one. Which molecule has the largest dipole? Well, we're looking for the 2 that are furthest away on the periodic table. They've all got fluorine in, which is all incredibly electronegative. So we're going to have to think about the shapes of these. So BF3, boron's only got 3 electrons in its outer shell, 3 bonds, which means it's going to be trigonal planar, which is symmetrical, so any bond polarities are going to cancel out, so there's no overall dipole. Sulfur fluoride, sulfur has 6 electrons in its outer shell, so it's going to end up with an octahedral shape again. It's symmetrical, so any bond polarities will cancel out, no dipole. CF4 is going to be tetrahedral in shape, so again, any bond polarities would cancel out. Chlorine has got 7 electrons in its outer shell, so that means it's going to form 3 bonds, and have 2 lone pairs left over. So that's the one that's going to have the largest dipole. In a molecule of a hydrocarbon, the fraction by mass of carbon is 9/11. What is the empirical formula of the hydrocarbon? So 9/11 as a percentage, or as a decimal rather than the fraction, is 0.818. So that means that 1 minus 0.818 is what's left as being hydrogen. Okay, then it is simply an empirical formula question. So we've got 0.818 divided by 12 and 0.182 divided by 1, which gives me a 1 to 2.67 ratio. If you times them by 3, that's the smallest number you would have to times this by to get a whole number, and then you get a 3 to 8 ratio, which gives us answer C. 30 centimetres cubed of xenon are mixed with 20 centimetres cubed of fluorine. The gases react according to the following equation. Assume that the temperature and pressure remain constant. What is the final volume of gas after the reaction is complete? So we need to know from the ideal gas equation that the volume and the moles are directly proportional to each other. We know we're starting with 30 centimetres cubed of xenon and 20 centimetres cubed of fluorine. We also know that 1 mole of xenon reacts with 1 mole of fluorine. So 20 centimetres of xenon will react with 20 centimetres cubed of fluorine, leaving 10 centimetres of xenon left over. Every time 1 centimetre cubed of xenon reacts, it's going to make 1 centimetre cubed of xenon fluoride. So we've got 20 centimetres cubed of xenon fluoride formed. So the total volume will be 30 centimetres cubed, which is answer C. Which of the following solutions would react exactly with a solution containing 0.05 moles of sulfuric acid? Okay, so we want to have exactly that. This is quite a tricky question. You've got to know that the formula for sulfuric acid is that, and you've also got to know that when an acid reacts with a base, that 1 mole of this reacts with 1 mole of this to form 1 mole of water. So the concentration of the hydrogen ions, every time one of these goes into water, it's going to make 2 hydrogen ions. So we've got that as being our concentration of, or our number of moles of hydrogen ions. Right, so if we react that with potassium hydroxide, that's just got 1 hydroxide ion. So it's going to be 50 times 1 divided by 1000, which is 0.05. There's not enough to react with all of these, so it's not that one. This one just has 1 hydroxide ion. This time we've got 100 times 2 divided by 1000, which is going to give me 0.2. Again, that's too much, so that's not going to react exactly. This one is going to give me 2 hydroxide ions every time I put 1 mole of barium hydroxide into water. So I've got 100 times 2 divided by 1000, which is 0.2. And because we had 2 moles, we can times that answer by 2, so that's 0.4. So it's not that one either. Let's have a look at this one down here. So we've got 50 times 1 divided by 1000, which is 0.05. But again, we're going to get 2 hydroxides for every one barium hydroxide. So we can times that by 2, which is 0.01. So D is the correct answer. In a car airbag, sodium azide NaN3 decomposes to form sodium, metal and nitrogen gas. The sodium metal then reacts with potassium nitrate to produce more nitrogen gas. If 2 mole of sodium azide react in this way, how many moles of N2 will be formed? Okay, so the first thing we need to do is to work out the moles of sodium azide, which is given to us in the question as 2. Then we need to have a look at how many moles of nitrogen are formed in equation 1. Well, if we had 2 moles of this to start with, every 2 moles gives you 3 moles of this. So that's going to be 3 moles. We also know that any moles of sodium, for every 10 we've got, will go on to form 1 more of these. Well, we've got 2 over here, so it'd be 2 divided by 10. So in total, the moles of N2 is equal to 3.20. Now the question asks us how many molecules of N2 will be formed. Now I've got the moles, I can work out the number of molecules. And I do that by timesing the moles by Avogadro's number. Which is answer B.